Right. So with us today is Mona Morsy. Am I pronouncing your name right? Yeah.
Good.
So Mona is visiting us from Marseille in France, from the Vegan group, who's been working on high resolution spectroscopy behind high contrast imaging systems, specifically focusing her work on young Jovian, spectroscopy of young Jovian planets. Before that, though, Mona actually did a lot of work in other areas of planetary science. She did an internship at JPL, working on Jupiter with Glenn Orton. She did then proceeded to do an internship here with our own Connor Nixon, working on his work. Was it on Titan?
Yeah.
That you worked on? Yeah, exactly. Yeah. Modeling of Titan. So yeah, so Mona has a lot of different experience in different areas, and she's just finishing up her PhD now in Marseille, looking at what comes next for her postdoc work. And she was at the SPIE meeting in Montreal and came down to do a little East Coast tour with us. So she's going to present on her PhD work here. So take it away.
Okay. Hi, everyone. I'm really happy to be back at Goddard. So I'm a final year PhD student working at the Laboratoire d'Astrophysique de Marseille, south of France. And I'm working on the development of a prototype instrument for the direct characterization of young giant exoplanets. Here is a presentation of the team. So the PI of the HiRISE project is Arthur Vigan. We also benefit from the knowledge of people working before on the sphere instrument. So we have Ketil Dolen and Anne Costi. And we have also a research engineer, Maxime Lopez, and myself. Actually, this is a picture at Goddard when I was working in a LiDAR prototype instrument with Dr. Chaoli-san. I will first start to talk about high contrast imaging. So you can see, so for ground-based observation, if you combine adaptive optic and coronagraphy technique, you can achieve a planetary contrast of 10 to the minus 4 to 10 to the minus 5 in the dark zone here. And by adding a post-processing step here, you can increase the contrast by a factor of 10 to reach a planet contrast of 10 to the minus 4 to 10 to the minus 6, which is enough to detect young giant exoplanet of a few Jupiter masses. Once you detected the exoplanet, what we would like to do is to do some characterization. But with the instrument I presented before, such as the VLT sphere IFS, you can see that we can only do first order characterization because we have, with this instrument, a very low resolution, and we miss some molecular features such as water. So we need high spectral resolution to, to do better characterization. So here you can see the spectra of an IFS on the IFS instrument of sphere with a spectral resolution of 50. And you can see that the spectra is not really well resolved. And by increasing the spectral resolution, for example, here it's an example taken with Ceres, with a high spectral resolution of 100,000. This is not the noise, it's really the spectral features of the planets. Also having a higher spectral resolution would make sure that we are able to see small events happening, such as the spin of the planet, thanks to the line broadening in the spectra, but also the orbital motion, thanks to the Doppler shift. But in order to see these phenomena, we need at least to have a spectral resolution better than 10,000. So at the VLT, at the UT3, we have two instruments placed on the NASMIS platform. So on one side, we have the sphere exoplanet imager, and on the opposite side, we have the near-infrared high-resolution spectrograph CRARAS+. So the aim of HiRISE is to couple these two instruments to with optical fibers. So what the goal is to use here to detect a well-known young giant exoplanet and to direct it to the single-mode fiber and to route it until we arrive to CRARAS+. And HiRISE will benefit from the high dispersion, high contrast imaging of sphere and the high dispersion spectroscopy in CRARAS+ in H-band. So here is the UT3 at the VLT. So HiRISE will be a visitor instrument in this project at ESO, and it will be divided in three independent parts. The first part is the fiber injection module, the FIM, that will be inserted in a sphere. Then we will have a fiber bundle that will be routed around the telescope, and it will go to the CRARAS+ instrument, where the fiber extraction module will be placed on the calibration stage of CRARAS+. So here is a view of a sphere. And we will be placed here. So here you see in blue the HiRISE instrument. And we will be placed after the coronagraph, downstream of the coronagraph, after the extreme AO, and we will be in the IFS arm of sphere. So the bench will be placed vertically, as you can see, because we don't have enough space. It's pretty packed. And the goal of this fiber injection module is to redirect the light towards the FIM instead of going to the IFS. So here is the mechanical view of the fiber injection module. So when we will operate in HiRISE mode, we will insert this vertical bench inside the IFS arm. And thanks to a pick-off mirror, we'll be able to redirect the light. And then the pupil of sphere will be reimaged on the mirror mounted on a tip-tip platform here. Then the light will be recollimated thanks to an achromatic doublet, and it will get through here a dichroic. And this dichroic will reflect the shorter wavelengths to the tracking arm branch and will transmit the H-band to the fiber mount here. And at the end of this fiber mount here, the fibers will be connected to CRARAS+. So here, we started the first assembly of the fiber injection module at LAM in 2022. And here you can see the fiber injection module after we started the implementation and after anodization of the instrument. So yeah, this was during the phase where we started to put helicoils inside the mechanical infrastructure of the film. We also started to receive all the optics. So the dichroid has been coated by the Institut Fresnel in France and received all our custom optics by Optic Fichu, and we placed them in the clean room after some verification of the specification we have been asked. So we also started to develop, so HiRISE will have an electronic cabinet placed on the NASMIS platform really next to Sphere. And we started to gather all the electronic PLC that will get inside this cabinet. And we started also to test them in the clean room. And we worked with ESO to develop a GUI to control HiRISE. So this is the fiber bundle that we will use to connect Sphere and Cryoras Plus. It's a 80-meter fiber bundle that is manufactured by a company called FTO in Canada, and it's composed of several single-mode fibers from Nufer. Here, I will not detail everything, but here is the side of a Sphere. And the orange circle represents the science fibers that will go all through the fiber bundle to Cryoras Plus. So the goal is to use Sphere to detect a well-known exoplanet and to inject it properly in this science fiber and to direct it to Cryoras Plus. So as you can see, the challenge is to route an 80-meter cable around the UT3. So it will be a bit of a challenge since we will not have any connectors in this fiber. It's only one piece that we will have to route around. So ESO has proposed this routing path, but it will be tricky. As you can see, we don't have enough space everywhere. And at some point, we will be going underneath the telescope. So here is a picture of Cryoras. Recently, it has been upgraded to Cryoras Plus. So now it's like using a new cross dispersion grating stage and new detectors. And the HiRISE fiber extraction module will be located at the very entrance of the instrument. It will be a very simple system and it should be completely passive. I've been working on upgrading the transmission budget and compared it to the previous one done by the former postdoc. We expect a throughput of 2.5% in H-band for HiRISE. But as you can see here in purple, the contribution of the fiber, like the coupling of the fiber, is a limitation to the transmission budget, but I would like to explain why. So coupling the PSF of a telescope into a single-mode fiber is challenging. It's really challenging, but it's really due to the intrinsic properties of the single-mode fibers. They are designed to only accept quasi-Gaussian modes and a flat wavefront. But also on ground-based telescope, we have central obstruction and spiders that affect the array pattern of the telescope, and this impacts the coupling efficiency between the PSF of the telescope and the single-mode fiber. So a former study made by Gilles Houghton had shown that for HiRISE, in order to achieve a coupling efficiency better than 95% of the maximum into the single-mode fiber, we must center the planet's PSF on top of the single-mode fiber within a specification accuracy of 0.1 lambda over d. So in order to fulfill these needs for HiRISE, I've been working to develop different techniques to center perfectly the PSF into the single-mode fiber. So for that, I've been working with a high contrast imaging testbed called MITIC in Marseille. This test bench is used, we upgraded it in order to emulate the HiRISE setup that we will use on Sky. So here is a more clear view of MITIC. So you have mainly two blocks. The first one is the telescope simulator. So we have a laser that generates a PSF, and this PSF is the stellar PSF that we will use in our setup. And here in the pupil plane, we have the SLM, space light modulator. It's very similar to deformable mirror. And because on MITIC, we were not able to create an off-axis planet, we use it to create replicas of the stellar PSF. And one of these replicas, satellite spots, will be used to be the planets in our system. Here we have an AO stage using a Zelda mask and a classical Yo coronagraph that we will not use during the tests on MITIC. And in blue here, I've been working in the implementation of the fiber injection module here. On the pupil plane, we have a tip-tilt mirror, and here is the tracking camera. And by scanning the tip-tilt mirror, we are able to inject light into a collimator. And at the very end of this collimator, we have a focal plane, and a fiber bundle is connected here. And the ends of the fiber bundle is divided into different sections. Some sections are,
I'm sorry.
Yeah. Some sections are connected to calibration sources that retro-inject light into some of the fibers. We use that for one of the strategies I've been developed. And because MITIC is monochromatic, we are not able to use a spectrograph. So we connect two of the fiber into power meters. Here is a view of the fiber bundle we have been manufactured to do some tests on MITIC. It's a very simplified fiber bundle. So it's single mode fibers. Cladding to cladding is 125 micron, and the core of the fiber is approximately 4 micron. The science fiber on MITIC is connected to a power meter, and another dedicated fiber, the centering one, is also connected to a power meter. However, just keep in mind that for high-rise, the science fiber will be connected directly to Crarias Plus, so it will prevent any verification during the observation. So that's why we came up with other fibers in order to develop strategies to center properly the planetary PSF on top of the science fiber. So the first tool is, so when I say we would like to place the fiber on top of the planet, the fiber are static, but what we do is we move the focal plane by moving the tip-tilt mirror. The second thing is the planet will be very faint, so we'll not be able to see it, even if we use a centering fiber connected to a power meter. And the third thing is, the first step is to retrieve the position of the fibers on the tip-tilt reference axis. And we could also follow the PSF on the tracking camera. So what we do is by scanning the tip-tilt mirror, we build what I call an injection map. And here you can see a normalized, rescaled injection map of the stellar PSF recorded into one of the centering fiber on MITIC. And you can see that in black is the fiber core diameter, and in red is the centering specification we aim to achieve for high-rise. So it's very challenging. So this is a core step I do here, because if I go for this sample, well-sample injection map, it took more longer. And so I do it coursely. And after I created another tool, so I tried to to optimize the injection. So to refine the injection, I used an algorithm, what I call like optimization injection is based on an Eldermid function. And then I'm pretty sure that I maximize the injection into my fiber. The other tool I built is what I called an interpolation function. So I would like to link the position measured on the tracking camera and the command of my tip mirror in order to be able to place the stellar PSF at any position in my camera field of view. So here, this map represents the residual map of the interpolation function as measured on the tracking camera. And the color bar represents the uncertainty error of my tool. So we can see that we are mainly better than the specification accuracy of 0.1 lambda over d here, but that a zone remains inaccurate with an error higher than 0.3, but it's due to the shape of the PSF. In this region, my PSF has coma and some other aberration. So when I do a Gaussian fit, it's biased by the shape of my PSF. So this I understood why. Here, I will only talk about one strategy. I will not present the others. The first one is the one that we are looking for on high-rise and we might use. It's the one involving only two fibers, the science and the centering fiber. So the first step is to really well calibrate the distance core to core between the two fibers. This is the first step. So it's a blue box here. And then is to do the first two steps, doing a coarse injection map and refine the injection by using the optimization, injection optimization. So at the step 3, we are able to place accurately the stellar PSF on top of the centering fiber. And here on Mythic, I was able to verify this step. And we will also be able to verify it on high-rise. And after this step, everything should on high-rise will be done blindly. Because at the moment we switch to the science fiber, we are completely blind. So on Mythic, I developed the tools and the strategies in order to have a confidence that if we use that tools blindly, we will be able to place accurately the planet on top of the science fiber. So the next step is to switch to the other fiber by applying the offset that we pre-calibrated during the day. And here you can see the planets here. So on Mythic, I could take an image of the planet and the stellar PSF and calculate the distance. And then I give this distance to my interpolation function, and I retrieve the comments in tip tilt that I need to apply to my mirror in order to move the stellar PSF at a position where the planet will be injected into the science fiber. And at the end of this step, I redo an injection optimization. So I have an epsilon value, and this epsilon corresponds to the distance between, correspond to the distance before and after my optimization. And it tells me how far I am at the end of this procedure from the core of the fiber. And the smaller the epsilon is, the better my procedure is. And then what I did is I wanted to test the robustness of my procedure. So I repeated this step 100 times. And I calculate my success rate. So how many times I'm aiming to place accurately my PSF on top of the science fiber. And it's what I did here. So the first thing what I did is here I fixed an angular separation between my planet and my PSF my planet and my stellar PSF of 10 lambda over d. And then I moved my planet around my star. And for each position, I did 100 times the procedure I told you before, and I calculated the success rate. And I compared the epsilon success rate to different specification accuracies. So you can see that 0.1 lambda over d, the specification has been given by the former postdoc by his simulation, is a bit challenging to have. So in average, if we do not take into account this gray zone, we are around 70%, but we are highly better if we go to 0.2 lambda over d here. So I was very curious about this drop here in this region. So what I did is I selected the angle that was in the middle here, 90 degrees. And I decided to also do it for two other angles. So what I did is I took 3 angles, and I decided to move, like to change the angular separation, because I was curious. It was like, is that because we were very close to the star, or it was linked to the tip-tip mirror accuracy? So I did that, and I saw that for the angle that was inside my gray zone, here we had a success rate that decreased as a function of the angular separation. So I was wondering why this would happen. And it's linked to the zone I showed you previously in my interpolation map, where I had coma and everything, because it's where my planet were at 90 degrees. But still, for the other angle, 0.1 lambda over d is quite a challenge, because the thing is, on Mythic, I calibrated the bench and I characterize it, but we are also limited by the jitter of the PSF. We have some vibration. The bench is not controlled either in temperature or humidity. We have a drift of my PSF during the time. So yeah, the stability is something that is not, that we need to take into account when we do the performance test on Mythic. So I will just do a conclusion on the performance test made on Mythic. I said that 0.1 lambda over d, in average, we have 70% of success. But if we move to 0.2 lambda over d, we have a better success rate. But on Mythic, we're mainly limited by the off-the-shelf component we use, the alignment, the test bed limitation, as I said, and the accuracy of all the tools I've been developed. So the interpolation function, the calibration between all the fibers, all of them had uncertainties. So by adding them quadratically, you don't need, you must not go over 0.1 lambda over d, but it's a bit difficult. But on HiRISE, the fiber injection module will be implemented on the Sphere arm, and Sphere is a very stable instrument with high quality optics and an extreme AO, so we should be very stable, not limited by the jitter of the PSF in Sphere, in theory. For now, the strategies that we are looking to, that we are aimed to use, will be this one that I presented, like using the centering and the science fiber. But we may loosen a bit our specification accuracy to 0.2 lambda over d. It means that we will have a less coupling efficiency, but up to 63%, which is not dramatic in our case. We will be able to characterize our exoplanets, but we will need to increase our time of observation in the at the observatory. just quickly, the expected performance of the of high-rise in H-band. So here we compared the performance of high-rise and Cryo Plus standalone. So here it's for a bright nearby exoplanet compared to very similar to Beta Peak. And here is the expected SNR for 2 hours integration observation for Cryo Plus and high-rise. And here the blue one, maybe you will not be able to see, it's from the Mordassini exoplanet population model. And it's just illustrative, but it's just to see that in this region, sphere is limited. It's not able to go for smaller angular separation and high contrast. And Cryo Plus will be also limited by its Macao AO system for smaller angular separation and high contrast, while high-rise will gain in sensitivity a factor of 2, almost 3 for small angular separation and high contrast compared to Cryo Plus. And on top of that, we see that Gaia will allow us to have a better knowledge of the astrometry, and that we could use combining, so we could use the Gaia astrometry knowledge for high-rise in order to place the fiber at the right location in order to detect planets, young giant exoplanet at small angular separation and high contrast. So this shows the potential of high-rise in H-band. So yeah, so just to finish, to conclude, we need a high spectral resolution in order to improve the characterization of young giant exoplanet, but also to boost their detection. It will open new opportunities to understand the formation mechanism of these exoplanets. High-rise will offer, so I would like to say that combining high contrast imaging and high dispersion spectroscopy has really started to emerge as a very powerful technique to characterize young giant exoplanet, and high-rise will offer a very unique opportunity on the VLT to couple 2 flagship instruments, Sphere and Cryo Plus. High-rise has already been accepted as a visitor instrument by ESO. We started the assembly, integration and test phase at LAM in Europe, and we aim to deploy the instrument next year in February 2023. So please stay tuned for the first slides of high-rise next year. Thank you.
All right. Thank you, Mona. Thanks a lot. We have obviously some time for questions here. You can either put the questions into the chat, or we have some claps online. So put some questions if you have them into the chat, or you can raise your hand using the reaction button at the bottom of Zoom there to raise your hand. Do we have any questions?
I have a question.
Yeah, we have one in the room. First, we'll start with Scott in the room. Feel free.
Yeah, so obviously the major focus of this is optimizing fiber coupling efficiency. You are not running EFC like a dark hole digging algorithm, right? I'm curious, because as you pointed out, fiber coupling efficiency is driven by basically how similar the electric field is to the fundamental Gaussian mode. And when we dig a dark hole, we're doing the opposite of that, right? We're moving away from that intentionally. I'm curious, has anybody done analysis to understand how, if you were to be running EFC, how that would impact your optimal coupling efficiency?
Yeah, I have a, this curve here, as you can see. So in green is with no coronagraph, and the 2 others are with an APLC and the CLC. Mm-hmm. And you can see that you lose in coupling efficiency. even if the transmission seems better, you would lose into coupling efficiency. But this was made for the VLT pupil, so it might be different. But I'm not sure that this simulation has been done with other pupil of telescope, because you have the central obstruction, the spiders, but the pupil of the VLT is very specific, I would say.
Yeah, I was more curious specifically about the shape of the DMs when you do waveform control, because it will impact the geometry of the PSF. In weird ways.
But we didn't do simulation on coronographic.
Okay.
I know that other projects use a coronagraph, but even not KPIC, I think they're not using a coronagraph. So KPIC Keck at Mauna Kea, I don't think they use a coronagraph because of the coupling efficiency issue.
Yeah, that's fair. Thanks.
Great. Anyone else online have any questions?
I have some questions, but I'll be in the room in like 1 minute.
Okay,
you guys
Tyler,
on the-
you're, yeah,
E115, Tyler.
E115.
Tyler wants to ask this question first.
Yes, you want to, okay. Anyone else besides Tyler want to ask questions?
I have a question.
Yeah,
It's
so-
not a science question, but are there any like current plans or like expected synergy with web and Iris?
Yeah, I think Arthur is planning to also use James Webb to have better knowledge of the astrometry of the planet also. But I think it's a bit more difficult. But yeah, if we could make ESO and NASA, it would be nice. Yeah, it's planned, but maybe first we will go with Gaia. And after we could switch to GWST, yes.
You mean it for the initial astrometry?
Yeah.
That's what you mean, yeah.
Because the challenge also is like the better you know the location of your planet, and not the easier way, but then you could be able to really put your fiber where you want.
Yeah.
And then it's like the centering, like, because if you have any offset, then you can see that it's pretty exponential. So you lose pretty quickly the coupling efficiency if you're not well centered. Yeah.
I guess on that note, I'm curious, can the observations you do with high rise inform any of the precursor science for Roman?
I think Elodie Choquet is looking for that, but I'm not really sure.
Okay.
But of course, it will open the path for other instrumentation, like PCS and ELT and Roman. Yeah.
So I have a question in terms of the statistics on planets that you hope to be able to do.
Yeah.
You're looking at thermal emissions for most of these planets, right? In the H-band?
Which one?
Go down to the high right, that one, the
Yes.
H-band one.
Yeah.
So what age planets are you sort of assuming? You know what I mean? Are you most sensitive to with these sensitivities in this wavelength band?
Like the young giant exoplanet, I
Yeah.
think this one is a good target. So it's HR 9799. Yeah.
Yeah. So the black dots are all assuming sort of 10 million to 12 million years.
Yeah.
In that sense. Gotcha. And so based on these sensitivities for that age, how low in sort of mass or size?
I think it's Jupiter size.
Jupiter?
Yeah.
Okay. Are the
pretty
black
bright.
dots known planets or?
Because I was not able to so the overlap, but the blue one is based on a model made by
Yes.
Mordassini, and the purple one is the one made by Gaia. So it should be there. We should detect them with Gaia.
Oh, okay.
Yeah.
Yeah. Tyler, did you?
Hi.
Hi.
How you doing? Welcome to the room.
Thanks.
Did
I had
you
to
want-
drive in.
Yeah, did you want to ask a question?
Yeah, that was really interesting. So I had a few questions. The first one is actually related to this plot. You know, these contrasts
Yeah.
that we get at 10 to the minus 5,
Yeah.
10 to the minus 6 is on the ground still
Yeah.
astoundingly optimistic.
Mhm.
But those are all accomplished in post-processing.
Mhm.
That is never raw. And that's using a lot of advanced differential imaging techniques
Mhm.
that you can't do with this fiber.
Oh,
So how
interesting.
do you achieve these contrasts with high rise from the raw telescope? Yes.
Yeah. So I think so. After we have the spectra from Claris Plus, we'll have, of course, the spectra like the. So we have dedicated fibers to sample the speckle fields, like
In
the
the
stellar
bundle.
speckle, yeah, in the bundle. But after, I think, for the data processing, so we do. Yeah, it's a good question, but I'm not really involved into this question, but I think I'm not sure. So we do the convolution to figure it out where we are, but for the really like the contrast, like if we aim to go to 10 to the minus 7 or 10 to the minus 8, yeah, I think we need a coronagraph, but we'll not use one. But maybe by doing RDI technique of data processing on the spectra after we aim to, I'm not sure about RDI, maybe we'll start with ADI and move to RDI after to achieve a better contrast.
Okay.
You also reject some starlight when you apply the fiber. Right?
It acts like a
little.
filter, yeah,
Not a lot.
yeah.
Has it been done before? I mean, is this the first instrument? That
No.
Orders of magnitude.
There is K-Peak and Subaru Ridge, but Subaru Ridge didn't publish any papers.
Mm.
But the people at K-Peak, Jason Wong, did a lot of that. Yeah.
Interesting.
So reach is, I'm on the. I work
Okay,
for
yeah.
Subaru, So it's I mean, that's really trying to hit the pendulum type things.
Mhm.
So it's a slightly different. Yeah, it's definitely a different case. Different way of thinking. So,
Yeah.
but they do that. Right. We have
Yeah,
a fiber
yeah.
in SkexAO.
And going to IRD.
It goes to IRD and it just gets deployed directly into the XAO.
Yeah, I talked to Olivier Guyon actually because I was curious about.
Yeah, and actually, well, the interesting thing is, the interesting thing for SkexAO is that you can actually still simultaneously image
Yeah.
with the spectrographs and everything at the same time,
Yeah.
which is kind of fun. I don't know that we've had any meaningful result come from that, but you know, we can pick the data.
Okay.
Yeah, so I do know that there is a contrast, especially when you try to do reference subtractions.
Yeah.
There is a contrast advantage to going to very high resolution because it gives you spectral information that allows you to
Depths.
post-process things because you are resolving lines.
Yeah.
So it's probably a lot of what's being relied on for the contrast estimates, I guess.
Yeah, but I'm not sure of what we will use because I'm not really involved into that now. But I know that maybe we use ADR or RDI or maybe other techniques that are just trying to develop.
Well, the key is probably those extra fibers you have in the bundle, right? I mean, because to do spectral subtraction, to try to subtract the speckle.
Yeah.
It needs to be very nearly neighboring,
Yeah.
because it's highly, otherwise it's highly uncorrelated. Even spectrally
Oh, yeah.
from, speckle across the field, so.
So has this been published on these simulations? Yeah,
The simulation has been
Yeah.
published by Gilles Autain. And yeah,
Okay.
it's this paper here.
Oh, I see. Ultimately.
Yeah, Gilles
Okay.
Autain. And now he's in Taiwan, but I'm pretty sure, like, if you have any questions, we'd be glad
Okay,
to
yeah,
respond.
Take a look.
Yeah.
Because it looks like he even has a test molecule that he's
Yeah.
assuming here. So there's a lot of information about the
Yeah.
simulation assumptions, Tyler, that might be in that.
Right, yeah. Yeah, that's interesting. I also had a question about Gaia,
Yeah.
the Gaia contribution. I was in the middle of getting from
Yeah.
through the gate when you were talking about that. So, yeah, sorry, couldn't be here the whole time. We are having a lot of success with Skexeo and Keras.
Yeah.
Doing Gaia and Hipparcos vetted target acquisitions to the point where we've gone from winning about 3 nights per semester to about 20.
Nice.
Okay.
So our proposal rate for getting telescope time has gone up significantly, because we can say with some confidence that there may be something there.
Yeah.
Help.
Yes,
Yeah.
it helps, apart from going, moving group and
For sure.
looking at a star. But anyway, I was curious if there's anything additional that you were getting out of Gaia, apart from just, the astrometry, knowing that there's something to go and look, because that's all we've been able to do.
Yeah, I think for now we were really interested into the astrometry of the precise. But for now, yeah, I'm not really sure.
Okay.
We are looking for something else. It will help us to have the very precise location of this small angular separation exoplanet from the host star. Yeah. For now, it's just that, but maybe after we'll be very interested to.
Yeah, you do still have even with the Gaia, anything you get out of Gaia, you still have a mass separation ambiguity, and so you don't actually know where anything is. In fact, I think what we're also finding is it's turning Gaia is helping turn XAO instruments into really good binary searchers.
Yeah.
Right.
But are you aiming for Reach to use Gaia also astrometry?
I don't know if the Reach folks have thought about that much, but it does obviously. But it's the same application in that sense, right?
Yeah, that's right.
You at least know that there's the stars worth going towards it. But anyway, where I was going with that is I was just curious, you still are planning to have to image it first before you put the fiber.
Yeah.
Okay.
That's right. Yeah.
Okay. That was the part I wasn't quite sure about. Okay. Cool.
So, well, the challenge with that, though, obviously, is if Sphere is not able to, or
to
anything
go
else
there.
to go there, then you don't really know where the planet is. in that sense.
But also Sphere is limited by the extreme AO at small angular separation and the static aberration.
Well, that's kind of why I was poking at the Gaia bit, because you can't, the point at which high rise crosses under the contrast curve of Sphere, it wasn't clear to me how you know where to put the fiber.
Well, if you do know the position angle.
The right assumption and the definition.
Does Gaia get you the position?
Not sure. I mean,
because you would
It's
imagine.
relative,
Right, if the stars. So then you would maybe could put the fiber sort of in consecutive
you
positions. You can hunt.
I think it's what they do in gravity. Plus,
I'm not sure actually. That's why I was curious, because we hadn't put a lot more thought into it beyond that. Beyond just being like, hey, these are good stars.
Yeah.
These will win us time.
Yeah.
But they also have more time than us. I mean, we will not have extra time during the observation. So we need to really do not miss the planet.
Yeah, no, I mean, we've been very successful in getting more reliable time.
Yeah.
With Skexeo. And by the way, they're all individual. No one's gotten like 20 nights. These are all like
Yeah,
a
that's it.
Spattering of individual like 2-night
Yeah.
PI proposals and stuff. So.
Okay, so let's pause for a second. And since
Is there anybody else?
I don't know, does anyone else online have a question to jump over to before the sort of inside baseball conversation continues here? All right.
Like this is our talk show here.
Yes, it feels like that a little bit. Okay, well, it is 11:57, so we're going to continue, but folks are happy to continue to listen in on the conversation or take off. I think I will stop recording now. Let's give Mona another hand here. So thank you. And we'll continue talking. I'll see if I can stop